A polymer is a very long molecule formed by the repetition of many monomers. These are molecules that can be linked to one another, forming a chain. The best way to write a polymer is to simply write the monomer, put it in brackets, and define the number of monomers it's composed of. When we link together two polymers that are made from different starting monomers, we can combine their respective physicochemical properties. These are called block-copolymers and have special behavior under certain conditions. One specific type of block-copolymers are those formed by a hydrophobic polymer joined together with a hydrophilic one. These are called amphiphilic block-copolymers, and it's interesting to know what happens once they're placed inside water. The hydrophobic block doesn't want to be in contact with water, so it will coil up. When more polymers are present, they will screen each other's hydrophobic block, self-assembling into a micelle. The three most common micelle morphologies are spherical, bilayer, and elongated, each of which depends on the starting block length of the polymers used. They are characterized respectively by their diameters, their thickness, and their length. We can direct the assembly of micelles by confining the polymer in a very small volume. This is done by dissolving the polymer into a volatile solvent, forming an emulsion of the solution with water and letting the solvent evaporate, effectively confining the polymer into very small droplets. Let's look a little bit closer at what happens in these small droplets. The amphiphilic block of polymer will want to be on the surface of the drop so that the hydrophilic part can be in water and the hydrophobic one can be in the chloroform. Since these droplets are evaporating, there won't be enough space for all the polymers to sit there. This triggers a phenomenon called spontaneous emulsification, which causes the formation of long fingers, which will then break up into micelles. Let's take a look at this happening in a video recorded with a fluorescent microscope. In this video you can see the chloroform droplets in black, which undergo spontaneous emulsification. They will break up into smaller droplets and form very long fingers from their surfaces. These very long fingers will then become worm-like micelles once the chloroform is completely evaporated. This is part of my PhD project, in which I study the formation of the micelles, I characterize them, I load them with radioactive particles, and I study how they behave in contact with cancer cells. In order to characterize the stiffness of the micelles, we developed a technique in which we perform nano 3-point bending tests. My project, called TRACE and TREAT, takes place in the Institut Charles Cedron in collaboration with the University of Delft and is part of the Curie Actions.